Okay. Okay, so last time I talked about various field theories involving various order parameters for mostly passive systems. So I want to start today by drawing the contrast between what can be expected for active and passive field theories of soft matter. So active versus passive. And this is mainly a list of things that passive systems have to obey, but active systems do not. So the passive case is constrained, and there's going to be a list of things here, all of which stem from a single basic property, which is the time reversal symmetry of the underlying microscopic dynamics. And if you want to know ultimately where that comes from, it comes from Newton's laws or possibly Schrodinger's equation. So in systems which are capable of reaching a state of thermal equilibrium, this underlying symmetry constrains in a strong way what the field theories can look like, in particular the way the noise terms can enter. So consequences, let's call this TRS, consequences of TRS, and I'm going to list them. The first of these is if you don't have time reversal symmetry, you have no reason to expect the existence even of a free energy that can be expressed as a functional of the order parameters as they are in space. So this is a general list of order parameters as it was last time. And later on, of course, we'll have many further examples of them. The second one is in a passive system, not only do you have a free energy, but in steady state, you have the Boltzmann distribution. Which I, of course, wrote down before. P0, so this is the probability of a configuration of the order parameter written as a function of spatial coordinates has got to be proportional to e to the minus beta f, where this f is that object there. And the third one, which I'm going to start a new column for, so these are all interrelated, is the principle of detailed balance. So this says that in steady state, this is the configurational probability of some configuration psi1, so some particular state, a microstate if you like, of the system, multiplied by this other p, which if you remember was a path weight. So this is the probability of going from an initial state phi1 to a final state phi2, given that I started in that initial state at time t. And this is something which Dan repeatedly mentioned in his lectures as well. I'm just formalizing it now. This has to equal the probability of starting in phi2 and transitioning from phi2 to phi1 in the same time interval. So the probability of seeing the system move from one state to another from 1 to 2 via any particular path is exactly that of the reverse process. And a less formal way of saying this is that movies look the same running backwards. So because the underlying microscopics is the same, in general, if you perturb the system, it may relax towards equilibrium. As it does so, you can see an arrow of time, an evolution caused by that process. But once you reach the steady state, if the underlying microscopics is reversible, then there cannot be any difference between movies that are run forward in time and movies that are run backwards in time. That is a fundamental property of the Boltzmann distribution in equilibrium systems. And the fourth, equally related, which I will finally prove for you in a minute, at least for an example, is the fluctuation dissipation theorem. Which I mentioned last time, and says that the noise terms in stochastic differential equations for the order parameters are fixed by the dissipative terms, such as the viscosity, diffusion constant, or mobility. So, 4 follows from 3 and 2. Fifth one, no circulating currents. In steady state. These circulating currents could be in real space, so if you see a bacterial system and you have a circular domain and this bacteria swing round and round in circles, as you often do see in bacterial colonies, we heard about it before, and the flocks, etc., not allowed in passive systems. And the same is true not just in real space, but in phase space. So any process which is a circulating current in the space of these configurations will violate this statement right here, because it tells you going one way around a certain loop of states is more common than going the other way around the same loop of states. Okay, so these are all things which are constraints on passive systems, which are not constraints on active ones. Erwin. I think that's a debatable issue. Well, if I have a passive system and I put it in an isolated box, it will still reach the Boltzmann distribution at the temperature corresponding to its initial energy. So I don't think I need a separate statement about that. In other words, in a steady state, even if, as long as the system isn't connected with, multiple reservoirs at different temperatures, a closed system will still reach this state. Just that you don't know quite what beta is until it's reached that state, if you see what I mean. Yes, well, I don't regard that as passive for these purposes. It's driven. It's neither active nor passive, but driven. Yeah. Sorry? Yeah, I mean, 5 follows directly from 3. Yeah. It's just a useful way to think about it. Yeah? Fine. It certainly would. I think that will become a lot clearer when I start talking about the active ones, because one of the main ways that I'm going to talk about creating active field theories, you start with a passive one and you start adding terms which break one or other of these assumptions. And very often, that's the first thing to go. So obviously, if you define a free energy by being the log of the steady state probability density, then it always exists. The fact is, though, in a equilibrium system, that's also minus kT log z. It's got all of thermodynamics sitting behind it. Yeah, it's just the log of this. Yeah. Okay. So now I want to just proceed, and this is again, before starting to talk about the active cases, what I want to do is something which was promised last time. which is a proof of this. And I'm not going to prove it in general, but what I will do is prove it for a particular model, and this is going to be model A. And I think that's because this proof is, if you've not seen it proved this way before, hopefully you may find it illuminating. At least I did when I first saw it proved this way. So, how do you prove fluctuation dissipation theorem? In other words, the relation between the noise amplitude and the dissipative terms for a field theory. And I'm going to do it for model A. So in model A, we have the following equation of motion. Phi dot equals minus gamma df d phi plus, and I'm going to introduce an unknown coefficient here, nu, times the regular character I introduced last time, which is unit white noise, Gaussian noise. So if you remember model A, it describes a passive system with a non-conserved order parameter that just relaxes according to the local gradient of the free energy towards a minimum of f. And because the system is not going to just go to the minimum of f, but is going to go to the Boltzmann distribution, I need that noise to keep it inflated, if you like. Now, having said that lambda is unit white noise, well, actually, first let's rearrange this as an equation for the noise, which looks a bit peculiar. Lambda equals 1 over nu times phi dot plus gamma df d phi. So that's a relation between, if you think of you can think of this as a path, it's a trajectory, and this is the particular noise function of r and t, which is needed to realize that trajectory. So because lambda is unit white noise, we know how to write down a probability density for lambda. So this I shall write with one of these p's. So this is the probability of a particular realization of this function of r and t. And it's the following. So some normalization here that I won't need to worry about. Exponential minus half integral mod lambda squared. The mod sign is not necessary because lambda is real, but I'll write it anyway. So that is the statistics of Gaussian unit white noise. In other words, this is like a separate Gaussian every point in space and time with unit variance. That's what this thing means. So if I know the probability distribution for lambda, and I know that lambda is equal to this object on the right-hand side, I know the probability distribution for the paths as specified by this thing here. So, and I'm going to put a initially unnecessary subscript f on this. This is the probability of observing a particular path, phi of rt. So some normalization which could in principle be different, but that won't matter. Same thing. Nu squared under here, which is that 1 over nu squared, integral phi dot plus gamma df d phi squared dr dt. Again, might put moduli signs there, but I didn't. So this is the probability of the path phi. So this is going to start at some initial configuration phi 1 and go to final one phi 2. So now I'm going to do something, and the reason that this f here is because that's the probability for the path in a movie running in the forward direction. What I'm going to do next is write down the probability under the same dynamics of seeing a path which corresponds to the time-reversed movie. And if I do a time reversal operation on this path, what I have to do is change the sign of phi dot here. This is some function of phi at each point, each slice in time, that's not altered by time reversal. So I can construct this reverse path probability. So this is forward. PR of phi RT. And this is the same normalization because the total number of paths, if every forward path is also a reverse path for someone else, if you see what I mean, exponential minus 1 over 2 nu squared integral minus phi dot plus gamma df d phi squared dr dt. So that's the probability of observing the reverse path in the forward dynamics, or you could think of it vice versa if you want to. Right. Now I can use this here because I have a forward probability and a backward probability in these two equations. The principle of detailed balance is extremely powerful. It says that these two probabilities must be related by a factor which involves the ratio of the Boltzmann distribution, Boltzmann weights for the initial and final states. Yeah. Oh goodness. No. Yeah, the initial and final states being interchanged, it doesn't. Yeah. Right. So let's look at this ratio. First calculate the ratio and then notice that it has to be equal to the ratio upside down of these two. Am I okay to erase here? So PF over PR. So you can expand out those squares there, and you've got a phi dot squared in both cases, and you've got a gamma df d phi squared in both cases. So it's only the cross terms which are different in the forward and backwards path. And by the time you allow for that, this ratio can be written in the following way. Integral from 1 to 2, just adding that to be explicit. The cross term there's two of them, and they've both got a 2 in, so I have 4 phi dot gamma df d phi dr dt. And I can integrate this. This is that's a constant, 4 gamma, bring that out the front. Phi dot df d phi integrated is over space and time, is actually the change in F, the free energy, between the initial and the final configuration. So this is equal to e to the minus 1 over 2 nu squared. Well, let's put the 2 up here, and the gamma F of the final state minus F of the initial state. And by detail balance, this is equal to P naught of the final state over P naught of the initial state. So 2 final, 1 initial. Well, that's lucky. I've got e to the minus something f here. And that's what I need in this ratio. I've got to have e to the minus beta f phi 2 minus phi 1. Otherwise, I can't do it. Okay? So 2 gamma over nu squared is equal to beta, or nu squared equals 2 gamma kt. So we've had that 3 or 4 times in the last lecture for the viscosity. Yeah. Yes, because I left the 2, of course. Well, I meant to cancel that. Yeah. So yeah. So we had that for the viscosity, for the diffusion, and here it is for a gamma-like thing. So, and this generalizes. I can do it for model B. It's more elaborate, obviously, when you have a conservation law there. But this is basically the fundamental connection. And many of you will have seen a quotes proof of detailed balance just by looking at the variance of some particle in a trap. And then someone says, oh, but this is true generally. Not very satisfactory if that was your undergraduate explanation of it. I hope you like this better. So likewise for conserved fields, etc., and indeed anything. So anything which can be written down with a Langevin equation as the stochastic Pde for the equations of motion, you can pretty much do the same thing, and you will find a connection through this kind of route between the noise amplitude and the dissipation. Yes. Yeah, okay, well, we could have a long debate about the names of things here. So this is a link directly between the fluctuation terms, i.e. the noise in an equation of motion, and the dissipation terms in the same equation. For that reason, it is often called the fluctuation dissipation theorem. There are other things which are also often called the fluctuation dissipation theorem, which talk about correlation functions in relation to response functions. So yes, many of you will be familiar with those, but this is what I mean by it for this course. Yeah. Okay. So the problem with active field theories is we don't have this. We don't have any of the 5 things that I said were consequences of time reversal symmetry, and so we have to work harder than would otherwise be the case. So, active field theories. And I should say, by the way, of course, we've seen one already today. The Toner 2 model is one of the things that I'm calling active field theories for this course. So stochastic PDEs. Yep. You mean, can I make any use of this for a driven system? I'm talking about active systems as distinct from driven systems. So I'm not talking about systems which have any kind of imposed external flux through the boundaries in these lectures. Obviously, some of the things I say will have relevance to that, but I'm not going to identify them. Suitable order parameters. The usual list: density, velocity, polarization, nematic, etc. And basically unconstrained by items 1 to 5. So given this absence of constraints, we have to think a little bit about how to construct these. So there are 2 approaches, both of which were foreshadowed in John's lecture earlier this afternoon. First one, which he didn't do for reasons that he explained, and I will barely do either, except in one example, which I will show you in the next lecture. So explicit coarse graining of some microscopic model. So the micro model typically involves interacting particles with some rules of interaction, whether that's flocking or whatever. And in principle, I can try to go through a process which John called kinetic theory, which would take me from equations of motion for individual particles to collective smooth variables like a density field and a velocity. So pro, unambiguous. If I do this successfully, I will have definite parameter values in my final equations. Con, I will remove an expletive here and just say hard work. To the extent that it's very often impossible for models you would like to do this for. And the other thing which John also mentioned, that is any particular model, so any particular micro model might miss something. Generic. Because our micro models are usually very highly simplified, and if you don't know what you might get, then you can't be sure whether you found everything. So the second route, which is again the one that John followed today for the Toner 2 equations, is top down, so the analog of what Navier and Stokes did. So 2 top down, I'll call this phenomenology. So as we heard, write all terms allowed by symmetry and conservation laws to some order in gradients and order parameters, powers thereof, and then add some noise. So this is an issue, of course, for the reason I've said. We can't just necessarily get the noise by inspection or by FDT. So an advantage, relatively easy, though it does require a certain amount of skill. And it is systematic to a given order. So it's your job to be systematic. In other words, to identify all the terms that actually are allowed in a given type of system that one is interested in. Against that, numerous unknown parameters. So all these phenomenological coefficients of these terms are separately negotiable. And also, as I've said, no FDT to guide noise. So this is something which is not taken as seriously as it might be, I think. As far as I know, the only really reliable way of getting the noise robustly correct in equations for active field theories is through a coarse graining route. I don't know any other way that allows you to be certain of what the noise should look like. Of course, you can guess, and there are many, informed guesses that are probably reliable in particular situations. Terms. Okay. So once we've got these, so I'm going to take a particular approach here, which was not obvious in what John was saying this afternoon. At least with a bit of effort, you can usually view these in a certain way. So the resulting stochastic PDE, or which is what I'm calling the field theory, is in these terms. Order parameters, time rate of change, equals a bunch of stuff which you might find in a passive model. So let's say effectively, and the word effectively is important here, some effectively passive contributions, and then something which is a list, so plus a list of activity parameters each with some term that is an explicit violation of time reversal symmetry. Violation. So not everyone thinks in these terms, but I find it useful. If you construct this equation with all the terms you can think of in it, you can try to write it like this. Gather in a big batch things which are allowable in a passive system, and then have a list of additional things which are not. And one of the advantages of that, of course, you can then always imagine these parameters to be small, and you should be able to connect your active field theory to a passive one and do some kind of perturbation theory. I'm not going to talk about doing that very much, but to have, at least in your mindset, a manifold of models that have a passive model as some end member can be a useful thing to do. And it's not always obvious what this end member should be. Julian? Yes, well, that of course is the problem, because if you have these effectively passive terms here, you probably know what the counterpart noise should be. And that's one guide to what the noise might be here. So let me put the noise in, but emphasizing that we don't really know what the noise is. So other things being equal, you might certainly choose the noise to be inherited from here. Erwin. Yes, but if you are doing this though, actually you just expand the parameters in powers of the dynamic variables, and you're saying I'm now going to work to a certain order in those. So it's like doing Landau theory for everything. And of course, that's restrictive. There will be many cases where that doesn't capture the whole of the physics, but hopefully that will give you most of what's going on in a particular system when the order parameters are not getting very big. So that's in the same spirit as how you might construct Landau-Ginzburg type theories for equilibrium. Okay, so a couple of notes here. The word effectively is very important in that equation, in that statement there. So this refers to the form of these terms, not to their physical origin. Yes? To what? Yes, it is. It's just the problem is that we don't have any clue how to calculate it unless we do root 1. So if you get a microscope model and you coarse grain it, you should get the noise terms as part of the output of your coarse graining operation. Because in equilibrium or near equilibrium models, we're used to using the FDT to fix the noise terms. The problem is in active systems, we don't have that crutch. So of course there can be noise terms associated with the active bits of this, but we don't actually know what they are. So this is a limitation of this second approach here. So what I'm going to say is that the effectively passive sector, so the stuff in this square box here, may include things which are implicitly active. So a lot of the physics of active systems, which comes from activity, could nonetheless end up living in this box by the time you look at the coarse-grained equations. So an example of that, which we will see in some detail in following lectures, is motility-induced phase separation. So this is something we'll end up describing with a conservative scalar phi. And this is sometimes called MIPS. And this is a phase separation which happens in active spheres, for instance, self-propelled active particles who don't have any kind of aligning interaction, so there's no tendency to flocking, but they do have a tendency to slow down at high density, and it will turn out that those undergo phase separations, which are purely active in origin, in the sense I have hardcore repulsive interactions between self-propelled particles. They can still phase separate, and the terms that drive that phase separation when we get to this point, actually through explicit coarse graining, will live in this box. So that's why the word effectively is here. It's a question of whether these terms could be obtained from a passive model, not whether they actually physically originate in some passive bit of physics. But this raises a question because there's this kind of blurring between what's active and what's passive here. So this is explicitly active, that may have active bits in it. Then one of the first questions you might ask here is when does the activity actually show up at all at this level? In other words, if it turned out that all my activity was in this box, and everything, I did some coarse graining, and every term that came out of my active model could be represented by a model with detail balance, free energy, and so on, then I'd have mapped my active system onto a passive model. Because without any explicit violations, then there are no violations. So that raises this question, which will raise its head a couple of times in subsequent lectures, when and indeed whether active terms control the physics. So and this I mean explicitly. So if there are no such terms present, of course they can't. But if they are present, they might or they might not. Yes. Yes. Sorry? Well, the trouble is because they're explicitly breaking time reversal symmetry, you cannot actually classify them in the usual way into dissipative and reactive terms. You can make efforts in that direction, but I don't think there's a clean statement of what these terms are. They're active terms, they're not really dissipative or reactive, because both of those concepts are intimately tied to the passive models that we're used to, I think. I mean, maybe there's some way of using that language, but I haven't thought of one. Okay, so there's a question mark here. So even if I have both sets of terms, you might worry how much these ones are going to matter. So, end of question. So just as a route map, so later lectures, I'm going to do the bottom-up thing. So route 1 for a dry active scalar, which will actually be a theory of this, of MIPS. So dry meaning no momentum conservation, scalar meaning the order parameter is just a density. But first, I'm going to give you a brief survey of some other cases. And this is going to be top-down only. So this is just to give you an idea of what is the variety of active field theories that you can get by the top-down approach, and also I'll try to be reasonably consistent in writing them in this sort of way. And because of that, I'm going to actually start with the Toner 2 model, which we heard about but was not written in that sort of way. Any questions? Okay. So, 1, dry flock. So John mentioned various bells and whistles that you can add to Toner 2, and this will be a particular version of Toner 2. It won't look quite like what he had, but it's essentially the same type of idea. Rho dot is minus div j, so particles are conserved. So this must be the current divergence of a current form. Rho is a density. Now John worked directly with the velocity field. I'm going to introduce something slightly different from that, because I prefer to think of flocking particles as having a direction, and then they move with the speed in the an average speed that's set by. So the average current is V0 times rho times p. So p, as introduced previously, is the average on a mesoscopic scale of a unit vector attached to each particle. So this is a self-propulsive flux. Okay, so we're doing this top-down, and as John said, and there are these 3 terms involving different lambdas, which I'm not sure I've got exactly the same notation, but I'll try at least to echo what we had. P dot plus lambda 1 P dot grad P. This lambda obviously has to involve take in factors of V, and there may be factors of rho as well, so this won't be exactly the same, but it's a description of the same type of system. Lambda 2 P dot grad P dot div P, excuse me, P times div P. And I think these are the same lambda as before. Lambda 3. I'm going to put a factor of a half here because there's a P squared in there, but that's a detail. Equals. Now, departing from what we saw earlier, I'm going to make this look like a polar liquid crystal, which we talked about last time. So I have a polar order parameter. It's not conserved, and so I can write down something here which is basically is of a free energy like structure. These are all active terms. So, well, let me actually just write it like this. AP plus B P squared P. So, and I can have some gradient terms here if I want. Grad P, double contraction, grad P. I could have some other term which connects P to rho. That says that P would like to point up or down the density gradient if I have one. Now, this looks equilibrium-like, at least. In fact, the whole thing can be written as a free energy derivative if I wanted to. And so I'm going to assume that the noise here is the usual equilibrium noise, gamma, times vector unit wide. So this, if you like, is a standard H, so a molecular field or a free energy derivative for a polar aligning thing, liquid crystal. And there are various ways in which some bits of this can be absorbed into there, but I won't go into that now. That I mentioned as an aligning term, which would also be present in equilibrium in general. Okay. The fact is, though, that if I had a free energy like that, then you'd also expect, in general, a contribution to the current here driven by the gradient of the chemical potential. In other words, I'd expect something involving dF by d rho in this equation. So I'm going to add that now. Yes. Sorry? Yes? Oh, no, I don't have that. Yes, I'm sorry. It's going to have to be a... Yes, okay. Let me say d by dp of this. I do apologize. That's the thing which lives in the free energy. So I have to take its functional derivative, which is a bit of a mess, actually, but it's got 2 grads and 1 p. Yes. Let me make a note of that, as I did last time. That's half time. Let's pause for a second. Yes. In the free energy, it's like the square gradient term grad phi squared. Okay. That's what that is, and I've, of course, failed to differentiate it properly. Any idea what's going on?
No, I mean the lights are somehow randomly going on in
But also there's something about the air conditioning,
about that.
the central heating or the air conditioning,
Yeah, yeah. I mean,
because you know
conditioning is just ventilation. I mean,
yeah.
I talked to Navier.
It's interesting because there's this huge humming noise which comes usually out of those vents over there, and there's a small one from here, but there's a huge one from there. But I've not heard this lecture.
But I talked to Navier this
Yeah,
morning. She
yeah,
said, yes, you know,
yeah,
sometimes it's there, sometimes not.
yeah. Okay,
I
fine,
have no idea what.
fine, fine. Okay, 1 minute warning. Right. Okay, so let me carry on. So although I said I was going to do this top-down only, I'm going to simplify this using a piece of information which actually comes from the microscopic coarse graining, which I don't know how much of that we'll see, but I'm not going to do it myself. So at least in the simplest models of flocking, if you do this explicit coarse graining, you end up with a relation between these three parameters here. So this is the thing about having multiple proliferation of parameters when you do it top down, but sometimes there are things are more precise when you're coming bottom up. So this is what those suggest. Oh, Julien, congratulations. Needs a theorist in the end. Okay, so if you have that relation between lambda 3 and lambda 2, this is connected with a question which came up earlier about different ways of rewriting these different terms in terms of each other. So nonetheless, if you do that, p dot, and I've still got lambda 1, so this still breaks Galilean invariance, doesn't have to be unity here, p dot grad p, so this is the convective type term that John was describing. I can still write this as minus gamma df d phi 2kt gamma square root unit white. And this f here, which you think you might be able to guess purely from this part, sorry I didn't take that derivative properly, actually then it's possible to build parts of these terms, in fact both of them, into the free energy like term. So this is an example of an active terms here which under certain conditions at least can be taken into the free energy. And so this is what I was talking about here, of a term becoming effectively passive even if its microscopic origin is strictly to do with self-propulsion or activity. So this is the resulting f, and you won't be surprised by the form of most of it. P squared b over 4 p4. This is the bit I forgot to differentiate, so apologies about that. And minus w bar div p. So that's an unusual, div p times rho, excuse me. So we're getting terms in the free energy here which might look a little bit strange. And then this lambda. And again, you can see this isn't really a free energy because it's got a dissipative coefficient in it. It's got a gamma in it. Nonetheless, it is of a passive form, which is p squared div p. So this is, you can think of that as a coupling between the strength of the ordering and its splay here, but this is something you could call pseudo-passive. So if that term had gone away as well, then we'd have a passive model. Yes, sorry? Yes, of course. Just correct my notes. Integral. Sorry? Yes. And you've been here for 3 weeks. I've only been here a day and a half, and so I think I'm impressed with people's attentiveness at this point. Excellent. Okay. So this is just showing that active terms could end up in either place, and that they will have a different role in the final theory depending on which of these things happens. Now, there's something I should say. I was just about to say before the break, is if you think of this as if you think of the passive part of this as a model, a passive model to which I want to connect the active one in some limit, then this is where my comment about the apparently incomplete form of the current comes in, because I've got the final structure here. Rho dot is minus div j as usual. I'm going to write j equals two pieces, so an effectively passive piece and an effectively active piece. And j active we've already talked about, which is v naught rho p, so that's self-propulsion, that's clearly active. But there would in general, if I have a free energy like this, there would in general be a diffusive current driven by the gradient of the chemical potential. So I should expect passive, and this will be something like this, m grad df d rho, so the mobility times the gradient of the chemical potential, just as we had previously for any conserved scalar, and some noise to go with it. Unit white vector. But we're okay, because it's perfectly within our scope to set m equals 0. That doesn't stop it being a model. It makes it a rather unusual passive limit, though, because in fact the model is very singular in the passive limit if you don't keep a term like this. I haven't quite finished writing this down here. So official Toner 2 sets m equals 0 if we want to interpret it in this way as a passive model plus active pieces, which we don't have to do, but as I say, it's the way I'm going to be trying to connect things up. And so then finally we've got the p dot equation, which is already over there. Just writing it again because I p dot grad p equals minus gamma df dp, written correctly this time, plus the gamma noise. Okay, so we've got two activity parameters left now. They are lambda 1 and where's the other one? V0. Thank you. Right. So as I've said, though, the passive limit of this is a bit singular if you don't keep m finite. Nonetheless, you can see, though, that although, as John was constructing it, there was no hint of an underlying thermodynamic structure here, I can still gather the pseudo-passive terms and treat the active terms as something which breaks the time reversal symmetry of this other model that we might have more intuition for. Okay. So I'm obviously not going to say more about the actual behavior of the Toner 2 model, because John has already started doing that and will continue to do so tomorrow, I'm sure. So what I want to do now is just run through a few more examples. So that was a dry flock, also known as a dry polar liquid crystal, active. Example 2, and I won't spend as long on these other examples, dry active nematic. So I haven't said much about nematics, I'll just say what the order parameter is. This is Qij, it's a symmetric traceless second rank tensor. And its mesoscopic definition, analogous to this thing here, is here. Qij equals ui alpha. So alpha is a molecule, u is a unit vector along its direction, minus 1 over d delta ij. So this piece here makes this traceless, because that means that the trace of this vanishes even without the angle bracket. So when I average it, it still vanishes. So this describes a state of headless rods. which have a sense of an axis of orientation, but no sense of whether they're pointing up or down the axis. Or it could be headed rods, in other words, where there really is a vector with equal probability. Can't write today. Of being up or down the axis, the preferred axis. So when Q is non-zero, it has a largest eigenvalue, which is telling you a sense of direction in space, and that's the way in which the nematic is pointing. So I'm now just going to construct this by fiat as a passive model to which active terms will be glued on. So construct. And it's important, of course, that we, restrain ourselves to terms which are as low order in the Taylor expansion in order parameters and gradients as we can. Otherwise, as John said earlier, we could easily have an infinite number of terms, which obviously would take more than a lecture to put on the blackboard. Right. So what's the passive model look like? Well, Q is not conserved because things can change their individual orientation. So it's going to look rather like the passive P model did. And there's just one twist to that. So writing this in this form, minus gamma. Sorry. So this is a molecular field. Again, this is a derivative of free energy. And there's going to be plus noise here, which I won't talk about, but you can possibly guess what that might look like. Here's the molecular field. Now, you might just think this was a df by dq, which it basically is, but there's a projection piece here. So this bit just makes sure that q dot is traceless, which might not otherwise be I mean, I could always construct an F for which that was true by construction, but just to be on the safe side, let's make sure Q stays traceless by subtracting that off. So the typical choice of F for an equilibrium, so this is an equilibrium nematic without momentum conservation, looks like this. This is a function of Q, and we can also have a density, so we can talk about coupling Q to density fluctuations, and that's one of the interesting things which happens in the active nematic. So this is an integral, and this is the kind of thing we get. So trace Q squared, what I'm doing here is constructing scalars. F has to be a scalar out of Q. And I'm going to just carry on. B1 trace Q squared squared. So trace Q is 0, so I don't have a linear term here. I start with this. There's another one of the same order, B2 trace Q fourth. There's also a cubic term, at least in 3 dimensions, trace Q cubed. And those of you who know about nematic liquid crystals will know that this term causes, in 3 dimensions, the isotropic to nematic transition to be first order. So C goes to first order transition. In 3D. In 2D, it turns out that this term doesn't enter. Okay, and I can add gradient terms to this, k over 2. So there are various kinds of gradient term. The simplest is to write this thing here. There are in principle, there are actually 3 different coefficients of the gradient terms. This is all within the equilibrium model for nematic, so I don't want to go into too much detail there, but that's one way to capture some of the gradient information. I can also have a term which cares about whether Q is oriented along or against density gradients. That's going to have have 2 powers of the gradient of the density, because I've got to make a scalar out of a second rank tensor, and no, two powers of gradient, so it's actually grad rho. So Qij grad I grad j rho, and so on. So this term just says, okay, I mean, I could imagine a system which is about to phase separate in density, but no, let's be simple. Let's have something where density fluctuations always cost you money. So I have a positive quadratic term constraining rho to be close to 0. I'm expanding rho about some reference value as usual. Okay, so that's what the passive model looks like in this case. So let me write down a few more things about those terms, which I've mostly said, but should just make a note of. So the interesting case has a less than 0 to give me a nematic phase. B and C if I have, well, I don't need C. B positive. C can be either sign if I've got it there at all. So these control the bulk ordering transition. K is an elastic constant. Although there are more complicated terms available. W is lowest order of orientation to any kind of thing involving the density. A restrains density variations. Now, I've written this down for the passive model. Yes, please. Yes, well, I was just wondering about that. There are 3 elastic terms describing splay, twist, and bend. So probably I've just written down splay here, which is not really what I intended to do. So what I think sorry? Yes, so that's a slightly, I'm going to do that, but that's slightly ambiguous as to what this actually means then. It looks like a 3rd rank object, and then squaring it is a little bit awkward. I can certainly, what I'll do is I'll just check that out and put the right version into the written notes, which will be scanned tomorrow. Yes? Sorry? Yeah, B1, yes, yeah, yes, okay, no, that's a good point. Yes, yes, let's for simplicity, yes. Technically, there are regions where one could be negative and the other sufficiently positive, but that's not interesting from this point of view. Let me just make a note about the gradient bit here. Yeah, okay. So now, an interesting thing which happens here is if I start adding, I haven't written down the dynamics for rho yet. And when I do, there will be passive terms, active terms, excuse me. But, and it turns out that if you do this to leading order, in other words, you look at the lowest order active contributions that you can get in the equations of motion, including the rho equation, which is about to come, none of them are in Q. So the dynamics of Q is pseudo-passive, even if this was an active nematic system. So note, Q dot equation is pseudo-passive to leading order. Obviously, I could invent some active terms and put them in here, but what I'm saying is that the lowest order active term actually lives in the density equation, not in the Q equation. So I don't have to change this at all for the active case. So unchanged. So I turn to the density equation now, not unlike what I'm erasing here. So rho is conserved as ever, minus div j. So I'm going to have something like this. So this is a passive diffusive flux that you would have in a genuinely passive model, and then I can add an active term here. So this is a term which is going to break time reversal. Everything up to here doesn't. What I'm saying, the lowest order term that I can put in the equations of motion for a dry nematic that breaks time reversal is living here. So to lowest order in rho, q, and grad, I have J active equals some coefficient which I shall call zeta div q, because that's a vector and it just has one div and one q. There's nothing I could put into the q dynamics which wouldn't have at least two or at least three things, a div order parameter or the other order parameter, rho. Yes? I totally agree. And that will actually come up in the scalar case that is simpler to talk about later on when but I'll do in the subsequent lectures, having finished this overview, which I will do soon. I will zoom in on the case of a scalar order parameter, which, as you can imagine, is a little bit simpler than some of the things I've been talking about here. And that particular case will appear in what was then actually the wet scalar one. Yes, so it's perfectly true that I could have, but okay, so I have to be careful here, because when I said, I wrote down the equations of motion as, effectively passive and some explicitly active terms, but it's true that one way of explicitly breaking time reversal symmetry is to have the dynamics of Q and the dynamics of rho controlled by different free energies. So all the terms in either equation might look like they come from a free energy, but if they don't come from the same free energy, the system is still active. So that's the point you're making, and I completely agree with that. Yeah. Yes, yes, exactly. Yeah. Yeah. Okay. Right. Okay. So what's this look like? Well, just to see what the physics of that is. So if I have a state like this, where you can see there's a divergence of the axis of orientation, depending on obviously there's a sign parameter here, so I can draw this arrow in either direction, but I would have a J active along here. So what that says is that if I have an active nematic, the display of particles like this will create a flux either upwards or downwards. And similarly, if I have bend in general, so this could be in either direction. So you can see here at least how these terms break TRS. Because if I ran those moving backwards, I would obviously not see a flux in the upwards direction. If they're splayed like that, I'd see it in the other direction. So time reversal symmetry is broken explicitly by this term in a sort of graphic way. And as I've said already, any active terms in the Q dot equation are subdominant to this effect here, and left them out. So one of the things which happens, let me note a couple of active features. So there's one which you also see in Toner 2, which is called giant number fluctuations. So this coupling of the density through this active current to the orientation causes the fluctuations in rho to be much bigger than they would be in an equilibrium system. I won't say more about that now. And another, which I'll just squeeze in here. Actually, I'll put some pictures over here for it. So I'm just about to adopt this piece of the backboard. Self-propulsion of topological defects. So this is an interesting thing. Those of you who know pneumatics will know that this kind of structure with an orientational axis of order but no actual arrow along that direction, so a headless vector, can support topological defects, so-called charge half. They're things which look like this. So this is a minus a half defect. That's got threefold symmetry. There's also a plus half, which is like this. So I'm drawing the kind of local mesoscopic axis of the molecules here. And this point here is a plus half. And just to annoy you further by squeezing a couple more words in here, this has no reason to move. So this is static, if you like. But because of this effect here, you can see this is going to be zooming around. So this is self-propelled. And the sign of V depends on the sign of the zeta. Yes? Or two. So you first. So you're saying that if you had a vector coupling constant, yes, but you'd have to explain physically what the direction of this vector could depend on. And in this system, unless I have some external environment which defines a direction, then it can only depend on Q. So I think it's okay. But yes, no, it's true. Well, one thing I didn't say, obviously one thing you could do is you could put this whole thing in an external magnetic field or whatever, then you'd get exactly the kind of terms you're talking about. Yes, Austin. Sorry? So anything in F, because it's an F, respects time reversal. It's a scalar free energy constructed out of the order parameters, and if that comes into an equation of motion as a functional derivative, those terms can't break time reversal without assistance from somewhere else. They could do in the way John mentioned of having a different F in two different equations, but they can't do it by themselves. Do you agree? Okay, well, maybe discuss that later. Okay, so you can see this, by the way, if you get one of the physical realizations of the dry active pneumatic is where you put rice grains or so-called granular rods on a vibrating table, and they make ordered domains with this kind of pneumatic structure, and you can see these defects. They're just part of life for pneumatics, and you can watch the positive defects zooming around the system and the negative ones staying put. You can also see that in beautiful experiments by the Divergence group, now based in Santa Barbara, on thin pneumatic films, although admittedly those are not dry. Okay, how am I doing? I'm just wondering how far to go with this. I'm going to leave out the next one and just talk about the an active pneumatic that is wet. And I'm only going to sketch this. Yes. Yes. Which argument? Well, yeah, okay. So another way to break time resistance invariance is to break the fluctuation dissipation theorem. So for any free energy structure I choose, if I put the wrong noise in, or an incompatible noise, detail balance is also gone. Whether that describes an active model or something else that one would like to think of in other terms is debatable, but I agree that that's true. So yeah, but the free energy on its own, as long as you look after the noise, isn't capable of breaking it for you. Yes. Yes. So this, yeah, indeed. So this noise is basically involves that gamma, and as long as that gamma is not got some kind of memory kernel, then the noise is one. That's the usual statement. Yeah. Okay. Right. So I'm going to erase this and replace it by something remarkably similar. And then I'm going to finish surveying these many models. So incompressible, wet, active nematic, and I'm not even going to do this in detail. So one of the things which shows up in the Toner 2 model, which I presented as a model for a vector, a polar liquid crystal, is the self-advection term, the lambda 1 term, which says that basically you move along your own axis. And a nematic can't do that, because a nematic has an axis, but it does not have a sign to the sense of the axis. So I can't construct a vector out of Q. So Q doesn't define a vector. So there's no so-called self-advection, which would be the analog of P dot grad P in my version of the Toner 2 model. The form of this, though, is now I have to have some kind of co-moving derivative for Q. So I'm now coupling this to a fluid flow. So there's some big d by dt here, which I won't actually specify, but as we found for the passive polar system in the previous lecture, this is something that's going to involve the symmetrized and anti-symmetrized parts of the velocity gradient. And there's also, I mentioned a molecular parameter. There's also a slip parameter actually for nematics, so a molecular parameter here as well. So I'm not going to specify this, I'm just saying this is the type of structure that lives here. Again, minus gamma h. So that is the tensorial version of the molecular field that I had just erased here, with the usual noise. Well, there's some kind of second rank noise that I need in here, but that's obviously schematic. And then there's the Navier-Stokes equation. And if you remember in the systems I was describing, the passive systems I was describing yesterday, what happens in this equation is that as well as the intrinsic, the usual form of the Navier-Stokes equation, and with the noise stress, I also get a stress which comes from the order parameter. It's basically the order parameter issuing instructions to the fluid to tell it how to move to try to reduce this free energy. So this has a thermodynamic stress. Sigma q. And as many of you will know already, and certainly this connects with, I expect, previous lectures by Mike Shelley and others, the leading order form of this stress sorry, that's not just mixing my concepts. That comes from the free energy that was written here a few moments ago. So this depends on F. So it's some complicated combination of these parameters and the derivatives of F. We had this explicitly for the polar case yesterday, so I'm not going to write it out now for the nematic. It's similar but even more complicated. And then finally there's the active stress, which is what I was jumping ahead on. So again, you can ask, what is the lowest order term that you can put into the Navier-Stokes equation that expressly violates time reversal symmetry? And it's this one. Sigma active equals minus some coefficient zeta times q. And there could be higher order terms, but that's the leading order term. And so just to connect with what I assume has been covered in previous lectures, this sign of this active term here can again be positive or negative. So here's a particle, and it can either set up a local flow around it that's like that. So this is called extensile. And I can also have the reverse. This is my, well, let's just draw, I'm not going to put arrows on here, I'm just going to draw this as a rod. Or I can have the reverse. So this is the local effect of that stress created by a swimmer or a certain density of swimmers. This is contractile. And these correspond to different sign choices for this parameter. And so on. So again, in this equation here, in this model here, again, the dynamics of Q is pseudo-passive, even if the actual reason that the system's orienting could be because the particles are swimming rather than because they actually have thermodynamic interactions, modulo the comment that John was making. And the leading order, there's the lowest order active term in any of the equations is this active stress in the Navier-Stokes equation. So, in the last minute or two, I just want to conclude with a few comments about these various behaviors, and then the start of the next lecture, I will go back to root 1 and expressly derive by coarse graining the field theories related to active scalar fields. Okay, so and so on. So there are various other things I can do. I can couple P to Q. I can have systems with simultaneously polar and nematic order, etc. I can add, if I wanted, viscoelasticity to the Navier-Stokes equation. There's all kinds of things I can do. I would just refer to this review paper, which has probably been referenced already in this school. I'm not even sure Marchetti is the first author, but I consider her the organizer of this paper. Rev Mod Physics 2013, very famous, already 1,000 citations or something like this. So you can read about all of these models I've talked about so far in that review paper. Now I want to do, though, just before finishing today, I just want to list here with something that I'm conscious I haven't done, is to be very explicit, apart from a few things, about what kinds of new behavior activity can bring to these systems. So let me just recap a few of those and conclude. Recap of active effects. And I might add a few which are not really recaps. Giant number fluctuations I mentioned. So an extreme case of this, I I'm going to call unexpected phase separation. So phase separation, for instance, in a system of repulsive particles, where in a passive case you wouldn't really expect to see that. I can also get unexpected microphase separation. So microphase separation is where a system develops domains of very different density, but these domains remain of a finite size. So like a striped phase, a sort of lamellar structure, and these can arise, actually they are there in Toner 2 model, but they will also arise in the scalar models I'll mention later. So these are microphase separations which you wouldn't necessarily expect by looking at the effectively passive terms. If you write down a theory and it's got some effectively passive free energy, that might of itself try to make the system order with density modulation to finite wavelength. That's not uncommon, but actually what I'm talking about here, unexpected here, means that there's nothing in the free energy which suggests you're going to have a finite wavelength for your phase separated domains in the steady state, but that you do have that anyway. So that's another thing which activity can do. Circulating currents in steady state, obviously. Which the Toner 2 model can certainly do if you enclose it, as John was saying, in, say, a circular domain. Things will rotate either clockwise or anti-clockwise. Such currents are not possible in equilibrium, as I explained item 5 early on. So things like bacterial vortices, etc. And so I'm going to finish with a question, which will be gradually answered in the next lecture or two, which is how much of this physics, so question, how much of this physics is already there for the simplest active field theory, and of course it's my prejudice which says this is the simplest, but I think many people would agree that, especially given the complexity of some of the things I've been talking about, in the interest of simplicity, one would quite like to understand as much as we can using a single scalar order parameter, i.e. so phi is either a row or a composition variable. So that's the question which I will start to answer with the next lecture, and any more questions asked now.